Let's do another example with vector addition. Here we have a car that goes from 80 kilometers per hour in a direction of west 60 degrees north to 80 kilometers per hour in a direction of south 30 degrees west. And it does so in 45 seconds. And we want to find the car's average acceleration during this time. So the first thing I want to do is draw a sketch of what we have happening here. So we have an initial velocity of 80 kilometers per hour. I'll do this a bit thicker, 80 kilometers per hour. I'm going to draw our little car here. This is a view from the top, so top view. We have 80 kilometers per hour. We're moving at an angle of west. So this is west, 60 degrees north. So west, 60 degrees north. And then our car follows this trajectory. Remember, this is a view, a top view. This is a top view. And its final velocity is going to be 80 kilometers per hour. So again, this is 80 kilometers per hour. And now it's at an angle of south 30 west. So this is our south, an angle 30 degrees to the west. And once again, I'll draw a little car at the end. Again, this is a view from the top. And the question's asking us to find the car's average acceleration. So during this period of time, what is the acceleration? And remember, this is a period of time of 45 seconds. All right, let's get started here with step one. And that is going to be to reformat our vectors. So format vectors. And you'll see that the vectors that we're given, this one here, we like the format of it. It's 80 kilometers per hour, and its direction, we have it in a format that we can use. It's west 60 north. Remember, we want our direction in the east or west direction first, followed by an angle, followed by a north or south. So our first vector we're given, that's in good shape. And then our second one with 80 kilometers per hour, south 30 west, well, we're going to need to fix that one. So I'm going to write an equivalent vector. So first let me rewrite the vector as it's given. South 30 west, south 30 west. And what we want to do is have our west first and our south second. So as an equivalent vector, we have to rewrite this as 80 kilometers per hour with west and south. And what does our angle change to? Well, it's 90 minus 30 is equal to 60. So west, 60 south. And to do this, I want to show you this vector here. Remember, this was 80 kilometers per hour, south 30 west. And we have a new vector here. Remember, this is equivalent, but I just want to show you. With 80 kilometers per hour of west 60 south. So if we were drawing our vector west 60 south, what we'd be doing, I want to do this in a different color. How about in this blue here. So if I want to do this one in blue, I'm going to go 80 kilometers per hour west, 60 south, west, and then we're going to go 60 degrees south, then 80 kilometers. So as you can see, it's going to be the exact same vector, just written with a different notation for the direction, with our west direction first and then our south. And this is necessary for adding vectors, which we will do later in this example. So step 2, once we have our vectors formatted, is to organize our variables. So organize our variables. We need to know what we're given and what we need to find. So what are our givens? We have a v1, and that is this first vector. So our v1 is 80 kilometers per hour in the direction west 60 north. And we also have a v2, and that is our second vector, which is also this one, which we have rewritten down here. It's 80 kilometers per hour in the direction of west 60 south. And then the third piece of information that we're given in the question is a time of 45 seconds. So time is equal to 45 seconds. And what are we trying to find? Well, our unknown is going to be acceleration. So our acceleration is our unknown. And step 3, we're going to need to choose one of our kinematics equations. So choose an equation. And remember to do this, we look at our variables, v1, v2, t, and acceleration. And we're going to go over to our chart here, look at which equation uses these 3 variables. v1, v2, acceleration, and time. This equation here is going to use all 4 of those variables, so this is going to be the equation we're going to use, number 3. I've got it labeled number 3. Your textbook, your teacher might have these equations numbered differently, so it's important to look at the actual equation here. So because we have v1, v2, t, and a, that tells us to use equation number 3. I can draw a better 3 than that. Okay. And then that brings us to step 4, which is going to be to plug in our variables. Plug in variables. So I'm going to rewrite equation 3 here. I'm going to copy it from our table and rewrite it. So the acceleration is equal to v2 minus v1 all over time. And we want to plug in these variables into this equation. So we have our acceleration, that's our unknown, is equal to v2. So v2 is 80 kilometers per hour, the direction of west 60 south. Then minus, I'm going to do this in red, and you'll see later the reason for that. Minus our v1, which is 80 kilometers per hour, and the direction of our v1 is west 60 north. So west. And I'm going to actually do these in red as well, and you will see in the next step the reason for that. So, west 60 north. All over time, which was 45 seconds. All right, so we've got our equation with our variables plugged in. And you'll see what we're going to have to do is we're going to have to do some vector addition, or in this case, subtracting vectors. But the method that we have to subtract vectors is actually to add the opposite vector. So what we're going to do here is a step to rewrite the vector, but in its opposite format, and we're going to add it. So what we're going to have instead is we're going to add 80 kilometers per hour, and these directions, we're going to give the opposite directions also. So our west is going to change to east, and our 60 will remain the same, and then our north, got to do that in green, our north will become south, all over 45 seconds. All right, so what we have here are two equivalent expressions. So this vector subtraction is going to give us the exact same result as this vector addition, but we've rewritten it as an addition because it's going to be a lot easier to work with, and that's how we know how to do vector operations, is by turning our subtractions into additions and giving it in the opposite direction. And if you want to convince yourself that these vectors are the same, whether you're subtracting this or adding this, I encourage you to draw these out on a piece of paper, and you'll see that subtracting this vector and adding this vector are going to be the exact same thing. All right, let's move on now to step number 5, and that is going to be to perform the vector addition. So step 5, I'm going to perform vector addition. So we're going to perform vector addition. So I'm going to take just this vector addition here. I'm going to copy it and bring it up here for us to work with. Make it a little bit bigger also. All right, and I want to do some color coding to make this easy for all of you to follow along. So I'm gonna need 4 different colors here. So that west is going to be this light blue, south in purple, east is going to be this lighter blue, and then our south is going to be pink. Let's pick a nice pink here. All right, so hopefully you can see the differences in these colors. And we're going to add up these vectors using the method of vector addition that hopefully we are all familiar with. And that is I'm going to write this out here and then I'm going to explain it. So our first value, first we're looking at just this first vector, we're going to write in components. So this is our x component, or rather our east/west component. And then our north/south component. So in our first vector, the east component, or in this case it's going to be west, and because we're in a direction of west, that's why we have this negative. West is going to be negative. According to our sign convention, west is negative, east is positive. And if we're looking at the north-south, north is positive, south is negative. So west, that tells us the component is going to be in the negative direction. And cosine for our east or west components. And then when we're doing our north or south, we're going to be doing this in purple to show the south. So again, because it's south, we're going to do a negative and the magnitude of the vector multiplied by the sine of the angle. All right, and now let's do the second vector. So because we're going in the east direction, east is positive, and the magnitude of the vector is 80, times the cosine, because we're in the east or west component, times 60. And then for this north-south component, because it's south, negative magnitude of 80 sine 60. All right, and I'm going to write out these values again in an equivalent way. After we type these values into our calculator, we'll have negative 40, comma, minus 69.28 for our first vector. So again, these are the components of the first vector. And then for the components of the second vector, we have plus 40 and minus 69.28. And then we're going to add these up to get our resultant vector. So add them up to have a resultant vector 0 minus 138.56. And because this is a negative, it tells us that the direction is south. So our resultant vector is 138.56 kilometers per hour, and the direction is south. And there's no east or west component because this is a 0. So it's going to be just straight south. All right, now step 5 is that we're going to continue where we left off with the formula. So step 5, continue with the formula. So remember this formula that we had down here. I'm going to copy it, and we're going to continue where we left off. So we were trying to do this vector operation, and this was our resultant. So we are going to continue where we left off and plug this known value in now for the vector addition. And then we're going to divide it by 45 seconds. So remember, we found this vector addition through these steps to find our resultant, and now we're plugging that value into our formula. And now it's just a matter of plugging this into our calculator, and I encourage you to try this along with me. We get a value of 3.092 kilometers per hour per second. And the direction on that is south. So when we're writing our final answer here, we're going to write that A is equal to 3.1 kilometers per hour per second south. That is our final answer. To write a little statement along with it, that means in 45 seconds, so in the 45 seconds that we're observing the car has an average acceleration of 3.1 kilometers per hour per second straight south. So then looking back at our original diagram, that means throughout the 45 seconds that we're observing this car changing direction, the average acceleration acting on the car, or rather the average acceleration that the car experiences, is 3.1 kilometers per hour per second. So this acceleration vector, well, it's this acceleration that we see that the car experiences as it follows this change in direction. It's going to follow the car, and we're going to have this 3.1 kilometers per hour per second be with the car this entire 45-second span. And this acceleration is what causes the car to change in directions as we observe.